Good afternoon, everyone. I'm able to put this out a bit earlier than I anticipated because I was able to get hold of the junior round 2 questions pretty quickly with appreciation to some of my students. Now, for those of you who did take the SMO junior round 2 basically today, as this video is coming out a short while ago, I hope it went well. If you did as well or better than you had hoped, then congratulations. If you did a little bit less well than you had hoped, don't be too discouraged. Remember that the thing about round 2 with 5 questions is that there's always some degree of surprises, right? You can always have one more question that did not appeal to you and your score went down by 10 points. That sounds pretty dramatic, but it is just really one question. So don't be too discouraged if it didn't go as well as you had hoped, and if it went better, of course, that is great. Now, as I looked at this paper, my general sensing is that for those of you who have prepared well for the round 2 style of problems, it would be a bit more approachable because of the fact that some of the ideas are pretty standardized. There are no big surprises, unlike 2023. So it should be relatively possible also for you to discover the things you need to discover just by putting in enough time, or in some cases just putting enough work to solve the problem. So without further ado, I'm going to start discussing the solutions, beginning with the first problem, where the triangle, this is the easiest geometry diagram ever to solve. It's not really a geometry question. Right? There is a triangle, but that's all. Now I'm going to call it just ABC. And we want to find the shortest segment that divides the triangle into two parts of equal area. The first thing is that we roughly know how this could look like. For example, maybe I draw it something like this. Maybe I just cut it in half, which is very tempting. Maybe I can cut it in like this way. There are different possible viable options. However, the thing that is going to be true is that it is isosceles. I do know the lengths. If area is 1, these are both square root 2, and this is 2. It is symmetric, and so therefore I should really only have a couple of cases, because my segment goes from a side to a side. That's how you cut, right? You cut a piece of paper, you must go from one side of the paper to the other side. It may not be opposite sides, but they must be sides. And so by symmetry, there are just two cases. Right? So you cut from AB to AC, or the second is that you cut from AB to BC. Now these two cases, it is not very clear which is going to be strictly better, so we just have to check both. I do not need to check the other combination from AC to BC, because AC to BC, wrong side, I wanted to write it on the left. AC to BC is the same as the first case of AB to AC by symmetry. Alright, so let's start with the easier case, which I put it on the right, but case 2 is easier because that will give you a right angled triangle. So I think I'm going to do that first. So case 2, let the segment be XY, where X lies on AB and Y lies on BC. Now, the area is 1, and so therefore I have this small triangle is supposed to be half. So this one's easier because it's a right angled triangle. So I straight away know what is supposed to happen, which is that bx times by is 1. This is nice because xy can also easily be written in terms of bx and by, it is just going to be using Pythagoras. So xy is the hypotenuse of this right-angled triangle, and I want to make it as small as possible. It is not very surprising that as small as possible happens when bx is equal to by. You could justify it in a couple of ways, but the easiest would be just via AMGM. Two variable AMGM, however, is the same as completing the square, because x squared plus y squared greater than or equals to 2xy is just x minus y squared is greater than or equals to 0. So if you just wrote this down without stating AMGM, I think you'll be fine. If you just said by completing the square or something else, you are also fine. Okay, so this is the minimum for case 2, when bx and by are both 1. Now, this is not very surprising, because if you were to look at the diagram here, it is not surprising that maybe I would just want to draw something that is like this. However, it is quite promptly going to be clear that that's not the best, because I at least can just slice it in half directly. That should be better. So this would be the best if I cut between the two perpendicular legs. However, I think I can probably do better. So let's have case number 2. So I'll just draw another diagram. Now my order is mixed up because I wrote 1 and 2 in this way, since I kind of knew that I need more space for case 1. It is up to you which case you handle first. Now I want to cut between AB and AC. So I'm going to sort of do this. Now that doesn't really look like half, so maybe I should draw something that looks a bit more like half, just to not confuse myself. I call this X and Y, and I write the same thing again. Once again, I get AXY is equal to half. Now here's where the trigonometry would come in for those of you who are familiar, right? Because you almost immediately will want to use your half AB sine C formula and then the cosine rule with the 45 degrees. So if that is what you wanted to do, that is completely logical. I'm going to not do that. I'm going to just not do that because I want to stick to a method that is definitely okay for the SMO Junior. Okay, so what's my approach going to be? I'll start by just calling these lengths X and Y. Little x and little y. Again, I'm going to refrain from using trigonometry, so I'm just going to use ratio of areas. So AXY as a fraction of the whole thing is just going to be first compared to ABY. And then that you can compare to the whole thing. This is going to be AX over AB and then AY over AC. So it will be AX times AY, which is XY, over 2 root 2. And so this implies that my XY is square root 2. Now this makes sense. As a sanity check, the thing that I thought may work is this one, where x is square root 2, y would be 1. So it makes sense. xy should be square root 2. Now, I need to find an expression for the length of the segment xy, capital XY. To do that, I'm just going to drop the perpendicular here. This is a 90, 45, 45 triangle, and I will name that foot of the perpendicular Z. Why not? Call that Z. Now, immediately, the reason why this is good is that you have got this 90, 45, 45 triangle, the same as the whole big triangle. So the 1:1 to root 2 ratio will still apply. So AZ equals to ZX equals to X over square root 2. Now, of course, if you did this first, you would realize that, oh, isn't the area is half times x over root 2 times y. This happens again. This often does happen. So if let's say you realize that, I don't actually need that, you are welcome to erase this. You can leave it, of course, no one's going to bug you, but if you feel that, okay, this is looking too long. Right, so when you're writing your solution, you can leave unnecessary details in, but if you want to make things a bit easier to understand, you can always just also chop them out. So I'm going to sort of do that here, although now that would cause me to have to do a little bit of surgery to my solution. Okay, so Z, the foot perpendicular from X to AY. So this is actually going to be much shorter if I write it like this. That's why I want to change it a bit. So again, xy equals to square root 2 is still true, but now I can also have an expression for xy. Yz is y minus x over root 2, and so xy is xz squared plus yz squared which looks like this. I'll just expand this. You end up with x squared plus y squared minus square root 2xy, and square root 2xy is just 2. So fundamentally, this becomes the same task as earlier on, showing the comparison between the sum of squares as well as the product. We use AMGM one more time. Now this clearly is going to be smaller than square root 2, and so I just need to say that this is the minimum because equality can hold when x equals to y. Fourth root of 2, since xy is square root 2, and I want them to be the same. Now, this is actually not such an easy first question, in my opinion. It is not a very easy first question for two reasons. One is that the answer is not that easy to guess if you weren't thinking about like doing the algebra, you may immediately believe that you should just split it symmetrically in half. That's a very intuitive thing to try to do. Unfortunately, it turns out to be not correct, and so that is a little bit iffy because of the fact the answer is not obvious. Now, the other thing is that it's quite long, but in the context of the SMO round 2, it's not very long. Anything that you can resolve in under 15 minutes, which I've done here, I think is perfectly okay in terms of amount of work. Now, another reason why this is a bit strange is that there is now an actual geometry question here. So you kind of got two geometries, but the first one is algebraic geometry. You only really use Pythagoras theorem and area, which is not a lot of geometry. Whereas the second one is real geometry. Now, I'll admit that as a student, I would have found this quite difficult during my time in junior because I was just not very good at finding similar triangles and not very good with dealing with them. Let me give some suggestions as we draw this out as to how you could be a bit more targeted in your looking for similar triangles. Okay, so I will label it here because I know that BC and CD, I need to draw triangles that come out of them, and so I don't want to be cutting into my own question. Let's put F somewhere down here. And so BCF has to correspond to DEC. Now it has to correspond to DEC. BCF means that you can imagine first flip it over and then rotate it such that the BC lines up at DE. And that is going to be a little bit clumsy. Actually, no, we don't have to rotate it, my bad. Yeah, you don't have to rotate. BC corresponds to DE, DC corresponds to BF. So no, I only need to rotate it like this. So it kind of should look like that, maybe. Kind of. Now my diagram's not going to be perfect because I do not have a ruler. However, if you have a ruler, I'm sure you could use a ruler in the SMO. Make sure that your lines look as straight as possible. Just makes your life a bit easier. I'm going to do something just to remind myself of the two triangles that are similar. You should probably do that as well. And then I'm also going to use another color to represent AEF, which is the third triangle that is supposed to be similar to these two. Let me make my dotted line a bit more precise. So AEF is supposed to be similar to both BCF and DCE. Of course, you only really need to show one of them, right? Because if they are already similar, I only need to show AEF is similar to the first one, and then by default, it would be similar to the second one. There isn't really a better pair to use, so I'm just going to use BCF as my focus. BCF and AEF. Now, I didn't know this as a student explicitly, and so that could have been the reason why I took very long to find it, or find these sorts of things. But now whenever you see triangles like this, you notice that triangles that are similar, sometimes they are going to have a common point because there are not that many points in the diagram. Now the common point that they have here is F. Those two that I'm looking at have a common point F, and F plays the same role, right? F is going to be the so-called corresponding vertex. F corresponds to F. And so I can view this as a pivot point, and this BC just got rotated to AE and then scaled up. Now this is known as a spiral similarity. right? It's sort of like you have got F as the center, and then BC comes to AE. The nice thing about spiral similarity is that if you wanted to show FBC and FAE are similar, it would be equivalent to showing the columns FBA and FCE. In sanity check, they do look similar, right? Now, of course, when I say can show this, it doesn't mean that, oh, I'm done. I do need to show this. It's just that it gives me a different target. Because AEF seems to be a little bit hard to access. Now at least FBA and FCE both have some lengths that I can access. Because I don't really like AF or EF. But I'm going to have access to FB and BA. FC over CE. And of course the same thing with the angles, FBA and angle FCE. Those are more accessible because they are related to the similar triangles and the parallelogram. Okay, this is my thought process, right? None of this is going to go into my solution. Well, not exactly. None of it. It will not go in this order. I'm just going to now claim those similar triangles, FBA and FCE. Now, in order to show that, I need these two things. This is my SAS that I plan. And so I will present it in just those two steps. So how do I show that FB over BA equals to FC over CE? Well, BA is part of a parallelogram. I can shift it over to the other side. So then it would fall into the two similar triangles, which I already am given. Okay. So this FB over CD is now going to be equal to FC over CE. And this is by the given similar triangles. That's the length. Now the angle. Recall that we're using these because it's SAS, so it has to be that angle. In case you're wondering why not the other angle, if I chose this ratio to avoid AF and FE, I must use the angle between. So I don't even need to make a decision. I just sort of look at this and this and say, yeah, that makes sense. It's related to the angles in the parallelogram being summing to 180 degrees as well as the equal angles in my similar triangles. So I'll do a simple angle chase. So FBA, I split it into the parallelogram part and the similar triangle part. Meanwhile, I can work from the other end. So this is kind of a trick that we can use. We just work backwards and literally write them until they connect. I'll go with, okay, maybe I should not write it on the same line. It's a bit cluttered. I will write it below. 360 minus everything else. So 360 minus BCD, DCE, and BCF. Now I look at this and I try to find out how do they match up. There needs to be a 360 minus things, and ABC and FBC both can be written as 360 minus stuff. I can slide this to BCD, that settles half of it. And I can write this as 180 minus the other two angles in the similar triangle. I see that these match, and BFC equals to DCE certainly also matches. So that is good. Move this up. And again, I'll just write down that those two angles, that BFC equals to angle DCE, is because of the same similar triangles again. So hence shown by SAS, this is the so-called alternative pair of triangles. I switch from the alternative pair to the main pair. This always works, not just for this question. I'll switch back, and this will also help you understand this spiral similarity logic, why it works. Right? Why FBA and FCE would be enough to get to FAE and FBC. Essentially, it's just about these four lines coming up from F. The first thing is that I have now shown that the angle from B to A and the angle from C to E are the same. So these two are equal. Which would mean that BFC and AFE are equal. Just adding in the overlapping part, BFC and AFE. Now the other thing are the ratios that we found from the similar triangles. We get the new ratios, FB over FA. A tip is that you can just look at your statement. You don't have to keep going back to the diagram. FB to FA is FC to FE. I want to show BFC and AFE, the triangles, are similar, so I can just swap the orders around. And so again, by SAS, this would imply the triangles that I wanted, BFC, okay, I'll follow the order, BCF and AEF are similar. SAS. Okay, take note when we mention something like spiral similarity, you do not actually need to use spiral similarity. It's just that it would help you to know where to look, right? Which is a useful tool to have. Third question, this is not geometry. Prove that among the 7 triangles of area 7 in the area of 27, there are 2 that intersect in a region of area not less than 1. The moment I see this, I know it's not geometry. I know this is not geometry because the numbers are too ugly and the positions are too strange. And so I can't really find good positions for the triangles to do it in a purely geometric way. Now on the flip side, I would say that this is clearly a pigeonhole kind of problem. It's clearly a pigeonhole kind of problem because whenever there is something of the form, there are 2 that intersect, there are 2 that are the same. That is pigeonhole. Now, of course, pigeonhole if we just started off with, okay, so 7 triangles of area 7 means 49. Total area is 49, 27. So some triangles must overlap. That's obvious, right? There's just not enough space. But I want to say not less than 1. So it's not just enough to say they do overlap. I would like to make sure I know how much overlaps. So my idea is as follows. The square is like this. Now imagine we just have some triangles, right? So the triangles take up about a quarter of the area, so I'll just try to draw some triangles like conceivably a quarter of the area. This is not very to scale. If let's say I try to space them out such that they only intersect each other a little bit, then what I'm claiming is that you will not be able to have enough space after a while, which you can kind of see, right? If let's say these are not 1/4 size, these are way too small. And that's even if you try to use all the area available to you. So for example, if I say, all right, I will use this part here, and then after that I will also try to use like this. So I'm going to use all of as much as possible. I want them to overlap just a little bit and cover all the space. You can see that you kind of run out of space anyway. And that's because they don't just have to overlap. There's sort of 22 units of overlap. Now, here's how I'll describe it a bit more technically. But before I do the description, the idea is just 7 choose 2 is equal to 21. And 49 minus 27 minus 21 is not really minus 21. Is 22, which is more than 21. This is essentially the thing. So there is 22 units of overlap, of which there are 21 pairs of triangles that overlap. So some overlap will be large. That's the idea. Now I'll write it like this. So let the triangles be T1, T2 to T7. Of course, the sum of areas is 49. And so therefore, the area that is in overlapping parts so belong to at least 2 triangles. Straightforward, right? So that means this is the excess. Now I consider the fact that there are 21 of these pairs. So I'm now going to let the intersections, I'll call it Sij, be the intersection of Ti and Tj. And so there are 7 choose 2, which is 21, such Sij. Then the 22 units of area I'm going to call it region S. Not the amount, right? Just the region. So I can say that S is going to be the union of all of these. Now, union as in the intersections can intersect, right? So the intersections can intersect, but it is true that it comprises all of these. And so the area of S is going to be less than or equal to the sum of all of these. Okay, I should probably say something at the start. Like let this denote the area of region R, so that there's no doubt about what's going on. Where this S, I've already said, is at least 22. Here there are 21 of them that are summing to 22, and so therefore there will be those that are at least going to have 1 over there. You can say by pigeonhole. If you don't mention the word pigeonhole, I think it's fine. You can say it's clear. Okay, and so those triangles have an overlap of area greater than 1. Not SI, TI and TJ. This is a fairly classic example of our of our pigeonhole. So when you have this kind of examples, it's always about the numbers. So weird numbers, and then there are 2. Usually means that you should be finding a way to make it sort of just click but be 1 off. Pigeonhole is usually 1 more than would fit nicely. Question 4. Suppose for some positive integer n, the numbers 2 to the n and 5 to the n have equal first digit. What are the possible values of this first digit? You are in round 2. You should definitely just start listing first. List out powers of 2 and 5. See what happens. Okay, I can list out more powers of 2. But I don't want to list that many powers of 5 yet, so I shall just list out the powers of 2 up to here, and then go with the 5s. So my first hit, this is 3. Continue. Now, as you're going through this is a fairly boring task. You kind of see that it does not appear that there are others repeating apart from the 3 down there. This is not a proof, of course, but empirical evidence is very good for intuition, not for proving. Yet, sometimes the empirical evidence also is evidence not just of the correct answer or answers, but also of why the answers are what they are. Now, when I'm looking at them next to each other, what comes to mind is the fact that I'm only looking at each row. And when it comes to each row, I know that they multiply to a power of 10. And so it makes sense why, let's say, 100 and something got multiplied to 70,000 and something, because it's just a bit more than 100. But as it went up from 1 to 2, this sort of went down. from 78 to 39. So it makes sense that they are trying to complement each other in order to get a power of 10. And so the essence of it is something like you've got like 2.5 and 0.39 in a sense is around 1. That's the vibe that we're getting of why the front looks like what they look like. And then 3 times 3 is 9. So if I have 3 and a bit, I get 10. So I said 3 and a bit gives me 10. I think I know what to do. What I'm going to do is I will use scientific notation. Let's borrow something from our physics lesson, shall we? Now, of course, I will start with my claim that only 3 is possible. And of course, the example or the construction is that when n equals to 5, they both start with 3. It is not always true that you are asked to find all examples. So in this case, they only ask for 1. Maybe there are others, but that's not my concern. If they ask you for all possible solutions, then we have to do something a bit different. Okay, so yeah, as I'm recording this right now, I've just someone has just sent me a copy of the senior paper. I've not looked at it yet because I am talking. I will look at it later. And for those of you who are those of you who have taken senior and are watching this now, I hope it went well too. I have not much else I can say. Okay, on we go. Scientific notation. Now let 2 to the n be a times 10 to the r, and 5 to the n equals to b times 10 to the s, where our scientific notation is just that a and b are both between 1 and 10. Now then, of course, multiplying them together is what I wanted to say. So the product is a power of 10. Maybe I should just write it directly this way, right? No need to write it in that very clumsy manner. I'll put 10 to the n on the other side. So 10 to the n equals to this, which means that AB is this. Now clearly A and B cannot both be 1. And A and B are less than 10. This is the meaning of scientific notation. AB are not 1 because powers of 2 cannot be powers of 10. And so therefore AB is equal to 10. AB, of course, is going to determine the first digit, A and B. So suppose that 2 to the n and 5 to the n have the same first digit, k. Then it would mean that your A and B are both between k and k plus 1. Strictly less than k plus 1. These sorts of things don't matter too much. I'm just when you do enough math, you get very pedantic about this kind of inequality signs, but it doesn't actually matter that much. Okay, so k squared and k plus 1 squared is going to squeeze 10. And clearly this means k can only be 3. Done. Now some of you may have difficulty explaining this, and so you just describe multiplication. If the first digit is 4, the first digit is 4, when you multiply together, it is at most this, it is at least that. And then you're a bit worried, oh no, I didn't write it like this. Let me assure you that two things are true. First of all, there are many ways to express the solution correctly. And second of all, is junior. The graders know they are grading junior. They are in for a hard time because there are many students who write very long and unreadable essays because they are not familiar with math proofs and notation. If you have the correct idea, you are probably fine. Okay, so just relax. Unless you said something like, obviously, if it is 4 or more, the product is too big, and if it's 2 or, if you say obviously you're too vague, you'll lose some marks. But if you say anything to the effect of bounding like this, you are probably fine. Now that brings us to question 5. Question 5 is a Diophantine equation. And when it comes to Diophantine equations, integer solutions to an equation, I have no idea of the difficulty when I first see it. The thing about Diophantine equations is that it is impossible to tell how hard it is without doing some experimentation. And normally what I would do is to try to look for some small solutions, but I don't feel like doing them here because of this very mysterious 2003, plus this is power 4, not friendly for testing small values. What I like to do for such things is to just make things look nicer for myself. Now, what I mean by make things nicer for myself is that I want to make harmless modifications until it looks better. Harmless modifications are those where if the method was supposed to be method A will still work after my modification, except that now it looks nicer. Right? So for example, you say I'm going to try to take mod 2, mod 4, it would still work after my modification, which is that, well, first thing, I want to complete the square here. So the first thing I want to do is to complete the square, and then I am going to just let a equals to y plus 1. Okay, I'll fill that in later because I want to deal with the right hand side as well. Now the right hand side, likewise, I don't know what to do, but I feel like there's probably something hidden in here that I just can't tell. There is too much weirdness in this right hand side. And so what I would propose doing for this is that I also want to complete the square. I know it's a 4th power, but to complete the square, I can just focus on the front part first. Now, if I do this, that would be x to the 4 plus 20x cubed. That's what I want. And 100x squared. I'm left with, oh, that's great. I can go again. This is really great. So if I now let b be x squared plus 10x, actually, let's hold that first. I want to complete the square on this x squared plus 10x plus 2 squared plus 2000. Okay, so I shall let that be 2. Now this immediately makes life very simple. We just have a difference of squares equals to 2000. And don't forget that after that, we still need to check whether b can be equal to this. Whatever you have here, a is definitely fine. I'll just put this here as a note to myself so that it's quite easy to test out. It's also true that I can save a bit of time by saying that b is at least negative 23. So I do not need to worry about all the possible positives and negatives. Otherwise, it's a bit annoying. Okay, so what do I do? Difference of squares is what I want. And since b is greater than or equals to negative 23, I can write everything down. Just that it may take a while. So I'll write them all down. That is quite a lot. We just note also that a plus b and a minus b have the same parity, so I don't have to write every single thing down. In fact, I don't feel like writing the prime factorization. I think factors of 2000 are quite obvious. So I'm just going to say that since a plus b and a minus b have the same parity, and b is greater than or equals to negative 23 implies that the difference is greater than or equals to 2b, which is equal to 2b, which is greater than or equals to minus 46. We can just list out cases. So both must be even. I can start with the positives. Okay, effectively when both must be even, one way of thinking about it is that you give them a 2 each, and then what is left multiplies to 500. 500 is 2 squared times 5 cubed, so I expect 12 cases. Okay, now I'm starting to realize that I don't really want to deal with the negatives like this. So change my mind. I don't want to double because there's 12. I don't want to write so many down. I'm just going to just look for solutions where a and b are positive first. And so change my mind. If b is greater than or equals to 0, a plus b is greater than or equals to a minus b, and I'm going to just say that I look for positive pairs AB first. So I'll continue my listing now that we've said that. Factors of 500, maybe I should just list them for my reference. So you can do this sort of thing very slowly. You have got time in the SMO to work these kinds of things out carefully. Just don't mess up anything as far as possible. Of course, if mistakes happen, then that can't be helped. So I'm just doubling all these pairs that I have down there. And so this gives me A and B. A is just the sum over 2, and B is the difference over 2. Okay, so these are the positives. And for the negative cases of B, we know that only the minus 5 can work. It's within the range. And so we just check whether any of these are in the form of x plus 5 squared minus 23. So for the 7 cases, basically add 23 to everything in sight. And if I add 23 to everything in sight, see what happens. Only 1-to-1 works. Where x plus 5 squared equals to 144. And then now A is plus or minus 129. So x plus 5 is plus minus 12. A is y plus 1. And so x equals to 7 or minus 17, y equals to 128 or minus 130 are the two possibilities, and it just appears that you have got any combination being fine. Okay, and that is it. Once again, I feel that this is not the hardest paper for those of you who have done quite a bit of practice, in the sense that all of these ideas are not entirely new to the SMO Junior. It doesn't mean that not new ideas cannot be tricky, it's just that you each have a decent chance of solving each isolated question. Right? If you think you have a 60% chance of solving every question, that's not a very impossible question, but it just means the most likely score you have is 3 questions. So it's not individually hard, but if you're at a 60% per question, obviously your chance of solving all 5 is 60% to the power of 5, which is quite small. Some of you are also going to ask me about cutoffs. The answer is I don't know everything. All I can say is that in such a paper like this, I am sure that at least half of the students will be able to make reasonable progress. And so depending on your round 1 and round 2, depending on your round 1 score, what you need in round 2 will also differ if you're aiming for gold or top 30 or top 10. In fact, all of you guys who were there participating would have heard from your friends. So feel free to share in the comments section below if you have some sense of how everyone did as well. If you want to say lots of students did all the questions, or a lot of students did not solve question 5 or did not solve question 1 or fake solve question 3, if you have anything to share, please do, and we all can have a more complete picture of what has happened for this junior round 2. Okay, so now everyone can take a bit of breath finally, relax for a bit, unless you're taking the open round 2, in which case if you are taking the open round 2 next week, all the best. So thanks for watching. Once again, hope it went well, and see you back again soon.